Welcome to our deep dive into the cosmos. Today we're exploring one of the most fascinating phenomena in the universe, black holes. These enigmatic objects where gravity reigns supreme continue to captivate our imagination and challenge our understanding of the cosmos. From their formation in the death throes of massive stars to their potential role in the evolution of galaxies, black holes offer a glimpse into the most extreme environments in the universe. So, buckle up as we journey into the heart of darkness and uncover 20 mind-blowing facts about these mysterious objects. So, what exactly is a black hole? Imagine a place where gravity is so intense, so powerful that nothing, not even light, the fastest thing in the universe, can escape its clutches. That, my friends, is a black hole. It's a region of space-time where matter has been squeezed into an infinitely small point, creating a gravitational pull so strong that it warps the fabric of reality itself. Think of it like this. You drop a bowling ball on a trampoline, and it creates a dip, right? Now imagine that dip so deep that nothing can climb back out. That's kind of what a black hole does to space-time. It creates a cosmic sinkhole from which there is no return. Now, you might be wondering, how do these cosmic behemoths even form? Well, it all starts with a star much more massive than our own sun. You see, stars are like cosmic pressure cookers, fusing hydrogen into helium in their cores and releasing a tremendous amount of energy. This outward pressure from the nuclear fusion balances the inward pull of gravity, but when a massive star runs out of fuel, the outward pressure can't keep gravity at bay any longer. The core collapses in on itself, and boom! The star explodes as a supernova, one of the most powerful events in the universe. If the core is massive enough, the collapse doesn't stop there. It continues to squeeze itself into an infinitely small point, a singularity, and a black hole is born. Now let's talk about the event horizon, the point of no return around a black hole. Imagine you're approaching a black hole in a spaceship. As you get closer and closer, the pull of gravity gets stronger and stronger. Eventually you reach a point where the gravitational pull is so strong that even light can't escape. That's the event horizon. Once you cross the event horizon, there's no turning back. You're trapped forever, destined to be pulled towards the singularity at the center of the black hole. You can think of the event horizon as a cosmic waterfall. Once you go over the edge, there's no swimming back upstream. Chapter 4. The Heart of Darkness, the Singularity. At the very heart of a black hole lies the singularity, a point of infinite density where the laws of physics as we know them break down. Now we can't actually see the singularity because no information can escape from within the event horizon. It's like trying to look through a one-way mirror. But what we do know is that at the singularity, all matter is crushed into an infinitely small point. Imagine all the matter in a star or even a galaxy squeezed into a space smaller than the tip of a pin. That's the singularity. It's a place where our current understanding of physics simply can't explain what's going on. Chapter 5. The Black Hole Family Portrait. Types of black holes. Just like there are different types of stars, there are also different types of black holes, each with its own unique characteristics. We can classify them into three main categories: stellar mass black holes, supermassive black holes, and the elusive intermediate mass black holes. Stellar mass black holes, as their name suggests, are formed from the collapse of massive stars, typically a few times the mass of our sun. Then we have the supermassive black holes, the true titans of the cosmos, millions or even billions of times the mass of our sun. These behemoths lurk at the centers of galaxies, including our very own Milky Way. And somewhere in between these two extremes we have the intermediate mass black holes, the missing link in the black hole family portrait. Chapter 6. Stellar Remnants, Stellar Mass Black Holes. Let's start with the most common type of black hole, stellar mass black holes. These are formed when a star at least 3 times more massive than our sun runs out of fuel and collapses under its own gravity. Think of it like this. If the sun were to suddenly become a black hole, its event horizon would be only about 3 kilometers across. That's about the size of a small city. But don't worry, our sun isn't massive enough to become a black hole. It'll end its life as a white dwarf, a much less dramatic fate. Chapter 7. Galactic Giants Supermassive Black Holes. Now let's move on to the big boys, the supermassive black holes. These gravitational behemoths are found at the centers of most galaxies, including our own Milky Way. How did they get so big? Well, that's still a mystery, but astronomers believe they grow by gobbling up gas, stars, and even other black holes. Imagine a black hole with a mass millions or even billions of times greater than that of our Sun. That's the kind of mind-boggling scale we're talking about with supermassive black holes. Chapter 8. The Missing Link, Intermediate Mass Black Holes. Now, tucked away between the stellar mass and supermassive black holes are the elusive intermediate mass black holes. These cosmic middleweights are thought to bridge the gap between their smaller and larger cousins, but they've been surprisingly difficult to find. Astronomers believe that these black holes might be the seeds that eventually grow into supermassive black holes. Imagine a chain reaction of black hole mergers, with intermediate mass black holes merging to form larger and larger black holes over billions of years. It's a cosmic dance of epic proportions. Chapter 9. Small but Mighty, the Tiniest Black Holes. We've talked about black holes that are millions or even billions of times the mass of our Sun, but did you know that some black holes could be incredibly tiny? These hypothetical objects, known as primordial black holes, are thought to have formed in the very early universe, just moments after the Big Bang. Imagine a black hole the size of an atom, but with the mass of a mountain. That's the kind of extreme density we're talking about with primordial black holes. They're like tiny pockets of the early universe, frozen in time. Black holes are invisible to telescopes that detect X-rays, light, infrared, and other forms of electromagnetic radiation. However, we can still detect them. How? By observing their effects on nearby matter. Imagine a cosmic detective, piecing together clues to track down an invisible culprit. That's what astronomers do when they study black holes. They look for stars orbiting around seemingly empty space, or for jets of gas being ejected at close to the speed of light. As matter falls towards a black hole, it doesn't just fall straight in, instead it spirals inward, forming a flattened disk of rotating material called an accretion disk. Think of it like water swirling down a drain, but on a much grander scale. As material in the accretion disk gets closer to the black hole, it heats up due to friction, emitting intense radiation that we can detect from Earth. These accretion disks can be incredibly hot, reaching millions of degrees, and they emit radiation across the electromagnetic spectrum, from radio waves to X-rays. When massive objects like black holes collide, they create ripples in the fabric of space-time known as gravitational waves. These waves were first predicted by Einstein's theory of general relativity, and they were finally detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Imagine two black holes spiraling towards each other, getting closer and closer, until they finally collide in a cataclysmic event that sends shockwaves across the universe. These gravitational waves carry information about the objects that created them, providing us with a new window into the universe. One of the strangest predictions of Einstein's theory of general relativity is that time is not absolute, but is affected by gravity. This means that time slows down near a massive object like a black hole. Imagine you could travel to a black hole and orbit just outside the event horizon, while a friend stayed back on Earth. Time would slow down for you relative to your friend. You could spend an hour near the black hole, and when you return to Earth, years, decades, or even centuries could have passed for your friend depending on how close you were to the event horizon and how long you stayed there. It's like something out of a science fiction movie. If you were to fall into a black hole feet first, the gravitational pull on your feet would be much stronger than the pull on your head. This difference in gravitational pull would stretch your body out like spaghetti, a process aptly named spaghettification. Imagine being stretched thinner and thinner like a piece of cosmic chewing gum, until your atoms are ripped apart. It's not a pleasant way to go. The escape velocity of a black hole is greater than the speed of light, which is why nothing, not even light, can escape its gravitational pull once it crosses the event horizon. Think of escape velocity like this. If you throw a ball up in the air, it will eventually fall back down due to Earth's gravity. But if you throw the ball with enough speed, it will escape Earth's gravity and fly off into space. That's the escape velocity, the minimum speed needed to escape the gravitational pull of an object. In the 1970s, Stephen Hawking proposed that black holes aren't completely black after all. He suggested that they could emit a faint radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, is incredibly weak, and it's never been directly observed, but it has profound implications for our understanding of black holes and the universe itself. Imagine a black hole slowly evaporating over time, like a puddle of water drying up in the sun. It's a mind-bending concept that challenges our notions of how the universe works. At the center of our very own Milky Way galaxy lies a supermassive black hole called Sagittarius A*, or Sescar A* for short. This behemoth is about 4 million times more massive than our Sun, and is surrounded by a swirling disk of hot gas and dust. Astronomers have been studying Sescar A* for decades, and in 2022, the Event Horizon Telescope collaboration released the first-ever image of this cosmic monster, providing us with the first direct glimpse of a black hole's shadow. It's a remarkable achievement that opens up new avenues for studying these enigmatic objects. A universe of growth, black hole. Evolution. Black holes aren't static objects. They grow over time by accreting matter from their surroundings, like cosmic vacuum cleaners sucking up everything in their path. They can also grow by merging with other black holes, a process that releases enormous amounts of energy in the form of gravitational waves. Imagine two black holes spiraling towards each other, their event horizons distorting and merging, until they become one even more massive black hole. It's a cosmic dance of destruction and creation. Shaping galaxies. The influence of black holes. Supermassive black holes are thought to play a crucial role in the formation and evolution of galaxies. They can influence the rate at which stars form, the shape and structure of galaxies, and even the distribution of matter on the largest scales in the universe. It's like a cosmic feedback loop, with black holes influencing their host galaxies, and galaxies in turn influencing their central black holes. It's a complex and fascinating interplay that we're only beginning to understand. Unveiling the mysteries, the future of black hole research. The study of black holes is one of the most exciting and rapidly developing fields in astrophysics. With new telescopes and instruments coming online, we're poised to make even more groundbreaking discoveries in the years to come. Imagine a future where we can study black holes in even greater detail, unraveling the mysteries of their event horizons, their singularities, and their role in the universe. It's a future full of possibilities, and it's a future that I, for one, am incredibly excited to witness. The cosmic abyss awaits. From the smallest primordial black holes to the most massive supermassive black holes, these cosmic objects continue to intrigue and amaze us. They push the boundaries of our understanding of the universe, challenging our theories and inspiring our imaginations. As we continue to explore the cosmos, black holes will undoubtedly remain at the forefront of scientific inquiry, offering tantalizing clues about the fundamental nature of gravity, space, and time. Thanks for watching, and don't forget to like, share, and subscribe for more cosmic wonders.